Welcome to classes on chemistry, higher secondary first year, and today's class is on chemical bonding, and it is a very important class for entrance as well as class or board exam point of view. And in very often in the entrance exam there is a questions always asked up to question marks 20 or 16 is allotted in this chapter. So before coming to the main point of the chemical bonding, a lot of things, and it is very huge chapter, you minutely follow one of the very important trick. Very often you the student find difficulties in finding out the lone pair, and lone pair is a very important things. It needs to be calculated in finding out the many properties of chemical compound. So before going to the main topic of this one, and there are lots of key points in this one. We need to know the lone pair. What is lone pair? Lone pair is non-bonded electron pair which doesn't take part in chemical bonding. They remain as on the atom as non-bonded, and this pair of the electron is called lone pair. And this lone pair has a tremendous use in calculating or discussing a lot of properties. Number one, lone pair helps in very short, let me explain. I will explain each and every point on lone pair. And first of all, I will show the trick of finding out the lone pair and why this lone pair is very important in calculating or finding out the lone pair in a compound. Because with the help of this, without knowing this, we cannot find the hybridization of a compound, chemical compound. And it is a very important tool to find the hybridization. You need to know lone pair. Number two, in predictive bond angle. Whenever you will find the hybridization, bond angle is dictated. The extent of bond is dictated by lone pair. I will explain later on. Again, in predicting shape, sometimes you will find hybridization is same, but due to difference in the lone pair, bond angle is different. So again, lone pair is important in predicting the shape. And next one, in predicting dipole, it is a very important one. Which one has more dipole, which one has less dipole, and it's related to bond angle, is related to dipole. And again, lone pair is again important indirectly in calculating out the dipole moment of a compound. And next one is isoelectron structure. Very often asked in entrance, each and every point or very often asked in entrance. In the last year there is a question, I will explain. In the neet question there was a question, simple, just to calculate the find out. First to find out, you were asked to find out the lone pair of HCF2, I think. And isoelectronics, isostructural compound, isostructure of compound. Two compound may have the same hybridization and they may not have the same shape, and due to difference in the shape, though there is same hybridization, there is difference in shape occurs due to the presence of lone pair. And where predicting whether the two structures or two chemical compounds are isostructural or not, we need to know the hybridization along with number of lone pairs. If the hybridizations are the same and lone pairs are the same, then they are isostructural. Or hybridization is same, or in both the cases or both the structures, in all the structures there is no lone pair, then it is isostructural. So hybridization is the same, lone pair is same, or lone pair is nil, then the structure is same. Otherwise, hybridization may be same, but difference in lone pair may not give different shape, and they are not isolated structures. And then in boiling point, I will take example to find out which one has more high boiling point, which one is less boiling point. Again, this is in indirect way, is upon lone pair of electron. So first of all, I will find out I will show the technique. I will find out the hybridization. Now, what is hybridization? I am not going to details. So, if you talk about methane, and if you talk about NH4 positive, and CH4, we know that hybridization is sp3. So how we will calculate hybridization? Simple, you calculate the bond pair. Bond pair is 1, 2, 3, 4. 4 means S is always 1, and to make it 4, we give 3. Here bond pair is 1, 2, 3, 4. S is always 1, P is 3. So this is the way how to find out the hybridization. Now fact is that say it is ammonia. Now you will be confused how to find out the hybridization. You see, there is 3 hydrogen, means bond pair is 3. Bond pair is 3 bond pair, means it should be S, P is 2. S is always 1, sp2. But its hybridization is sp3. It is not. Its hybridization is sp3. Means somewhere inside this there is lone pair. So to find out hybridization, we need lone pair. Again, if you ask to find out this one, so again you will find here is bond is 2 bond, hydrogen 2 bond pair. So 2 bond pair is sp. It is not sp. Again it is sp3. Again, in case of this, if you calculate, there is 2 bond pair. So 2 bond pair is S and P. So its hybridization is again sp3. So we have seen in ammonia hybridization is sp3. Is NH4 hybridization is sp3. In NH4 positive, it is sp3. NH3, it is sp3. Water, it is sp3. H2S, it is sp3. So how can we conclude that these things, there is number of lone pair we can calculate, but with the help of lone pair we cannot calculate this hybridization. Now how we need to know the lone pair? So how we should calculate lone pair? This is the main point of today's class. So the first method I am explaining here, minutely follow. NH3. What is group number of nitrogen? It is 15. 15 means 15. 15 means outermost electron, valence electron is equal to 5. 15 group. You need to know the group number 15 or its configuration is 25. Am I right? So you write in this way, outermost electron is 5. Valence electron is 5. So valence electron is equal to 5. Valence electron is equal to 5. But one exception which I am going to explain, the number of lone pair calculation, that for hydrogen always you assume it has 1 electron, but for our calculation you always assume is 7. Am I right? This is exception. Always for hydrogen is assume 7. So valence electron of nitrogen is equal to 5 and valence electron of hydrogen is equal to 1 hydrogen 7 and 3 hydrogen is equal to 21. Am I right? So 2 valence electron, one is for nitrogen, it is 5, 1 nitrogen 5 and 3 hydrogen, 1 hydrogen is 7 is 21. So total valence electron is equal to 5 plus 21 is equal to 26, divided it by 8. So this is a very important method. You see, find the total lone pair of electron. In nitrogen it is valence electron, group number is 15, is 5, valence electron is 5, you just write 5, and for hydrogen is in 7 and 7 3 hydrogen is 7 3 are 21, so valence electron is 26. You divide it by this, you will get 3 plus remainder 2, and this 3 is the bond pair and remainder 2 electron is equal to 1 lone pair. So 3 bond pair, 1 lone pair. So in ammonia, which is not seen, there is lone pair is not or not, or there is lone pair or not, we can't see, we calculate there is 3 bond pair in 1 lone pair. So whenever you will find out the hybridization, so bond pair and lone pair should be calculated together. So how many lone pair and bond pairs are Altogether there is 4. So to make it 4, we need it is sp3 hybridization. So in a very fast manner, we can find out water, oxygen is equal to 16 group. So valence electron is equal to 6. Valence electron of oxygen equal to 6. 1 hydrogen is equal to 7. 7 to the 14. 14 plus 6 equal to 20. 20 divided by 8 is equal to 2 plus 4 electron, and 2 is the bond pair. 4 electron is equal to 2 lone pair. So you have got 2 bond pair, 2 lone pair. So in calculating the hybridization, we find out total 2 to 4. So to make it 4, we need sp3 hybridization. So sulfur, oxygen sulfur, again it is in 16 group. So valence electron is 6 and it is 7. 7 to the 14. 14 6 20. 20 divided by 3 is equal to plus 4 electron. This is 2 bond pair and 2 lone pair. That too gives you sp3 hybridization. HCF2. So if you draw the structure, you will find Hc and 2 bond. 2 bond means sp hybridization. No, the hybridization is not sp. Xe, xenon, kapton, radon, xenon, that are in 18 group, 0 group. So 18 valence electron. So valence electron is 8 and fluorine valence electron is 7. 7 to ja is equal to 14. 14 and 18 is equal to 22. 22 divided by 8 is equal to 2 plus 6 electron. So 2 bond pair, 3 lone pair. So if you asked how many lone pairs are there in xenon difluoride HCF2, we just calculate valence electron of xenon is 8 and fluorine is equal to 7. 7 to the 14 is equal to 2 bar divided by equal to this. The quotient give you the bond pair and remainder will give 6 electron equal to 2 electron equal to 1 pair equal to 3 lone pair. So how many pairs? Total 2 and 3 5. 2 and 3 5. The hybridization is sp3d. The hybridization is sp3. This is linear shape. Linear shape. Later on we will come in it. Equal to 7. 7 4 is 28. So you are getting 36. Again, beauty of this concept and trick is the axis tetrafluoride, xenon tetrafluoride HCF4. Here the valence electron is 8 and 7 valence electron is 4. Fluorine is equal to 7. 4 to the 28 equal to 36 divided by 8 equal to 4 the 4 that quotient give you the bond pair 4 and 4 electron left out. 4 electron is equal to 2 lone pair. So 4 bond pair and 2 lone pair. 2 lone pairs are there here in case of HCF4, and you are getting 2 and 4 6. 3 2 5 and 1 6. sp3d2 its square shape is square planar. Again the beauty, you see it, HCF4 is X valence electron equal to 8 and here is equal to 42. 42 and equal to 50 divided by 8 is equal to 6 plus twice electron, 6 bond pair plus 1 lone pair, that is 7 lone pair. 3 3 6 and 1 sp3d3, it is distorted octahedral shape. So these are the some way we can find out the lone pair. Now let us find out lone pair in another way. Say it is ammonia. What is ammonia? Ammonia is 5. Valence electron is 5. 1 2 3 4 5. Out of 5 there is 3 hydrogen, 1 hydrogen, 2 3. How many lone pair? 1 lone pair. 3 bond pair. 3 lone pair, 1 bond pair is equal to 4 total equal to sp3. Here, one thing you see here, oxygen, the valence electron equal to 6. 1, 2, 3, 4, 5, 6. Valence electron 6. How many hydrogens are there? One hydrogen, another hydrogen. This is bond pair, and you are getting this. 2 lone pair, 2 bond pair equal to total 4. Total 4 is again sp3. Again we have calculated lone pair in this way. But when we will calculate in this way, just if you want to find out sulfur dioxide, here in all the cases hydrogen is monovalent. If it is divalent, so now what's happened? The center is S and oxygen is on the both side S. So the center valence electron sulfur is equal to 6. So 6 electron, 2, 3, 6 electron. How many oxygens are there? 2 oxygen. Oxygen is divalent. So you make 2 here, 1 oxygen, 2 electron, 1 oxygen. So how many bond? You are getting 1, 2. How many lone pair? There is 1 lone pair. So 2 bond pair, 1 lone pair, sp2. If it is divalent, you don't assume 1 electron, you assume 2 electron, 1. If it is divalent, so 2 bond pair, 1 lone pair in sulfur dioxide. Again, if you were asked to find out hybridization of this, now what will you do? Say for carbon, the valence electron is equal to 4. Carbon is 14 group. You should know the group number. 14 group. 14 group means 4. Valence electron is equal to 4. So there is 4 valence electron. And how many electrons are there? 2 more. 1, 2. This 2 has come from here. Out of this, how many bivalent oxygens are there? 3. So 2 electron give 1 oxygen. This 2, 1, and this 2, 1. So you are getting 1, 2, 3 means sp2 hybridization. Am I right? Now earlier method, this carbon is equal to 4 valence electron and oxygen is equal to 6 valence electron. 6, 3 ja 18 and twice electron here. So you are getting 24 electron. 24 divided by 8 is equal to 3. Again you are getting 3 and this 3 is equal to sp2. In both the cases the method is same. If number of electron is negative is on the anion, you add up this electron in calculation either this method or in this method. And if it is plus, you subtract this plus, 1 plus subtract 1 from valence electron. I am showing you one example. Say NH4 plus is valence electron. It is 15 group. Am I right? 2, 5 valence electron. But 1 plus is there means 1 electron is lost. So out of 5 electron, we will assume 4 electron. So this 4 electron is occupied by 4 hydrogen. So bond pair is 1, 2, 3, 4. 4 bond pair means it is sp3 hybridized. So now let us come to the first one. It is 5, valence electron is 5, and for hydrogen it is 7. So 7 4 ja and plus 1 is means 1 electron less. So you are getting how much? 32. 32 divided by 8 equal to 4. Again you are getting sp3 hybridized. Predicting bond angle. Predicting bond angle. How it predicts bond angle? Say to predict the bond angle, we should know hybridization first. So if you calculate hybridization here, this is carbon, carbon is 4, 4 is attached with 4, means there is 4 bond, so it is sp3. Here already we have calculated, we have seen there is one lone pair in earlier cases. In both the method you calculate 2 lone pair and 2 lone pair. So we have got all have the same hybridization. Now if you see that it tetrahedral bond angle is 1093. So now you see why there is a difference in the bond angle. That difference is due to the presence of bond pair, lone pair. You should calculate the lone pair as the two method I have shown you earlier. Either method is helpful in finding out the lone pair. Here there is no lone pair, so bond angle will remain 109. Here there is one lone pair, it is a bit distorted, reduced to 109 from 109 to 107. Two lone pair further reduced to 104. Again, two lone pair further reduced to 92. So here in this case, you have got two lone pair and you have got two lone pair. But question is that why there is more reduction of bond angle in case of H2S, but in water it is 104, but in H2S it is 92. But both this structure has two lone pair. This is because oxygen is more electronegative than sulfur. Since oxygen is more electronegative, so oxygen attracts the bond pair of electron towards itself with greater extent than sulfur does. Sulfur has the same ability to attract the bond pair towards itself, but oxygen has the ability to attract the bond pair between O and H towards itself. Since oxygen is more electronegative than sulfur, so the oxygen will attract the bond pair towards itself at a greater extent to sulfur. So when it attracts the lone pair towards itself at a greater extent, means lone pairs will be somewhere very close to lone pair, and lone pairs will be very close to near. If bond pairs are very close to one another, there will be repulsion, and that repulsion gives rise to 104. But here this sulfur, due to electronegativity, more electronegative than hydrogen, it's also attacked the bond pair towards itself. So electron pair is here not at that close to oxygen, it is a bit further away. So when it is much closer, there is repulsion, the bond angle is a bit more. When it is less closer, less repulsion, so distortion of bond angle is more. If it is very close, due to high electronegativity of oxygen, more repulsion, bond angle is more. So sulfur cannot at that extent attract the bond pair towards itself, since bond pairs are a bit further apart, so repulsion is less. So less repulsion means more distortion, and bond angle is 92. So here in the second case, we can explain the lone pair also predict the hybridization along with bond angle. Bond angle changes a lot due to the presence of lone pair. Here is no lone pair, here is one lone pair, here is two lone pair, here is two lone pair, but oxygen is more electronegative than sulfur. So case 2 is over. Asks in the entrance. What is isostructure? If the two or more species have, if two or more species hybridization is same, lone pair is same, or lone pair is nil, then these two or more species are called isostructural. Say CH4, NH4 positive. You are asked whether these two are isostructural. Let us first find out hybridization. Carbon is valence 4, 4 with 4 hydrogen, 4 bond. So in both the cases, lone pair is equal to 0, lone pair is equal to 0. So you need to find out two things at a time. One is hybridization, other is lone pair. If you see both the lone pairs are same and hybridization is same, then these are isostructural. Now if you are given in this way, ammonia and this, now in this case you will get hybridization is sp3 here, but there is one lone pair because nitrogen is 5, 3 hydrogen is occupied, 1 lone pair is left, 1 lone pair. So since hybridization is same but lone pairs are not same, so these two species are not isostructural. Okay, so let us find whether these two are isostructural or not. So this it is 14 group, 4 electron, and here is 2 electron. How much electron? Total 6 electron. So 1 2 3 4 5 6. How many oxygen is there? Bivalent, divalent oxygen. So one oxygen occupied 2, another oxygen occupied 2, another oxygen occupied 2 electron. So it is 1 2 3 bond. 3 bond means sp2. Its hybridization is sp2, and there is no lone pair. Lone pair is equal to 0. Now come to this one, sulfur. It is 16 group, 6. So 6 valence electron plus twice electron is equal to 8 electron, means 1 2 3 4 5 6 7 8, and there is 4 hydrogen oxygen, 2 electron, 2 electron, 2 electron, 2 electron. So here in this case you are getting 1 2 3 4. 4 means sp3. So their hybridization is not the same, but both has same lone pair, so it is not isostructural. To be isostructural, their hybridization should be same and their lone pair should be same. So boron is 13. So its valence electron is 3, and here there is 1, means it is 4 electron, and that 4 electron is occupied by 4 fluorine. 1 2 3 4, that is total sp3 hybridization, and there is no lone pair. So here again it is nitrogen. Nitrogen is 15 group, means 5 valence, 1 is less, 4 valence, 1 2 3 4, occupied by 4 hydrogen. 1 2 3 4 means sp3, 3 and 1 4, no lone pair. So both the species have no lone pair and hybridization is same, that is their shape is same, hybridization is same, because lone pair is same or nil. So these two species are again isostructural. Hi, sulfur dioxide, water. If the question is like this, which one has more dipole? Again you need to find out hybridization. If you find hybridization, it will find it is linear, mu is equal to 0. This is linear, mu means dipole moment is 0. It is not linear, dipole moment is not equal to 0. It is not linear, dipole moment not equal to 0. We will be concerned with this. Out of these two, the result will come out. If you find out the hybridization of this, it is sp. Now if you hybridization this, so there this is sulfur, am I right? Sulfur is 16. 16 means 6 valence electron, 1 2 3 4 5 6, and it is divalent, 2 electron 1 hydrogen 1 oxygen, 2 electron 1 oxygen, am I right? So you are getting 2 bond and 1 lone pair. 2 bond pair, 1 lone pair, 2 and 1 3, it is sp2. sp2 hybridization, 1 lone pair. So come to this one. Here in this case it is sp hybridization and lone pair is equal to 2. Am I right? Earlier we have calculated. So each and everything is mainly depend upon the lone pair. Now we see the technique. So when we have calculated the lone pair, we have earlier shown you, if the lone pair is 1, ammonia, water, ammonia 107, water 104, more the number of lone pair, less is the angle. So its bond angle is it is sp2 should be 120, but it is less than 120 due to the presence of one lone pair, and its bond angle should be sp3 habit as 109, but due to the presence of two lone pair, its bond angle is this. Am I right? So we have got the bond angle of these two, but we are asked which has more dipole moment. So what is net dipole moment? Net dipole moment is equal to mu1 plus mu2 twice mu1 mu2 cos of theta. If theta is less, dipole moment is more. If theta is less, dipole moment is more. So we have seen in water bond angle is actual 104, and in case of sulfur dioxide it is less than 120, means its bond angle is more. Bond angle is less, dipole moment is more. So water has got less bond angle than sulfur dioxide. So water has got highest dipole moment in the series of the compound CO2, HI, SO2 and water. So you see lone pair again is applicable in case of calculating the dipole moment of a compound. Say if you are asked to arrange in boiling point, how can you explain with the help of the lone pair? So distinctly we have already calculated this has two lone pair of electron, this has one lone pair of electron, there is nothing. So how you now account for the higher boiling point with the help of the lone pair of electron? We know more is the association of the molecule, more is the molecular mass of the compound, molar mass of the compound, more is the association, more is the boiling point. So we will now decide how many hydrogen bonds are there possible in all this. All this has the ability to form hydrogen bond. Here in case of water, this. So here due to the highest electronegativity, high electronegativity of oxygen, it pulls out the electron pair towards itself, so partially negative and partially positive. And another thing is that there is two lone pair of electron. So two lone pair of electron and two hydrogen will form 2 plus 2, 4 hydrogen bonding in one water molecule. 4 hydrogen bonding. And here one HF, so that H from right side and one H with fluorine of other one HF will form 2 hydrogen bonding. Here there is 3 hydrogen, but due to low electronegativity of nitrogen, only this lone pair will contribute 1 hydrogen bonding, and here out of these 3 another hydrogen bonding is possible. So you are getting again 2 hydrogen bonding here in this case. But due to the, so we are getting some contradiction with these two, but due to the presence of this high electronegativity with the fluorine, hydrogen bonding extent in HF is more. So this is the highest and this is the second and this is the least in terms of bonding point. Am I right? So with the help of this trick of the lone pair calculation, we can explain the hybridization, we can explain the bond angle, we can explain the shape, we can explain whether isostructural or not, we can explain the higher and lower boiling point, we can explain the melting and boiling point of the compound. Hope you have understood the class with utmost importance, and it is very important for entrance point of view. In the next class I will explain the percentage of ionic compound, the percentage of ionic characteristics of a compound, how much percentage of ionic compound, ionic characteristics is there, how much covalent compound is there. In details I will come up with the next class. Hope you have enjoyed the class.